Next up is the spring force. All right, clearly it's a force due to compression or extension of a spring. And a spring is what you think it is, just a coiled up piece of wire that is kind of stretchy. One property of a spring we need to think about is that any spring has a natural length. All right, so if we just take a spring, coil up a piece of wire like that, if you were to measure, you'd say, okay, it's at some length L naught. Okay? I'm going to call it L naught because the length is going to change. So we'll call that sort of the natural length or the resting length, just if you held it like this. There's your L naught. Now, if you take a spring like that and clamp one end, and the other end is the origin, well, we always draw our problems in physics, right? So we would draw it and say, there's a heavy wall, that means the clamped end. And here's our other end. And if I said the origin, I must mean to draw an axis, x-axis, and here's the end we're going to attach things to, and that must be the origin. Okay, so we set that up. I can actually set that up over here. Here's another spring, better for the demo. Again, just a coiled up, stretchy piece of wire. And I'll set it here, and I need to clamp one end and call that the origin, or call the other end the origin, right? So here is my clamped end. And for the origin, see, we're going to label and draw an axis here, plus x. And then here is where I'm going to attach it. In this case, means I'm going to grab it, so we'll call that the origin. So the way a spring behaves is that if we pull this now to positive x, so my fingers are going to apply a force, the spring is going to pull, I'll feel a force on my fingers, and which way is that force? It is in negative x, right? The spring pulls back. So if I pull and extend the end of the spring to positive x, push the force I feel, negative x. If I compress the spring, if I push the end of the spring to negative x, I feel a force, but this time it's pushing me back to positive x. So a spring makes what we call a restoring force. It has a position that it wants, the origin, and anytime you move away from that position, it pulls back. If you move to plus x, the force it applies is to negative x. If you move to negative x, the force it applies is to plus x. Because all a spring wants to do is be at its natural length. So if we want to write that in terms of physics, it's called Hooke's law, which is the spring saying, let me be my natural length. And it's desperate too, so I'll put exclamation point. Right? So Hooke's law then, F, and you put minus kx, where k is the spring constant. Right? And let's think about what unit the spring constant would have to be in. Well, if this is newtons and this is meters, then it's in newtons per meter. Okay? So every spring has some spring constant in newtons per meter. This one has one. This spring over here has a different one. And the spring constant is not negative. It's a positive value. It's just a property of the spring. But the negative sign we put here reminds us that the force is the opposite direction to the displacement. Okay? Now, in most problems, or in a lot of problems, you won't really have your spring nicely laid out on a flat surface. Usually, your spring is hanging like this. So now we'll put the spring on a rod. And pretty much nothing is different, right? It's just hanging. It's got the same natural length. But, again, there's usually more going on. Usually you have a mass on the spring. So here, this little hanger has a, well, there's just the hanger for now. And you see what's going to happen when I let it go. The spring got a little longer, right? So it kind of looks like L naught is changed, but L naught can't really change, right? And that's a property of the spring. It's changed because this is pulling down on it. And then you'll usually have a weight on it, right? Like that. And now it's even longer. L naught is changed again, or the length of the spring has changed again. But there doesn't appear to be any force because this isn't moving. The sum of the forces on the mass is 0. So I just want to explain what you have to sort of think about when you hang a spring vertically. So let's take this same spring, and I'll just kind of draw it in the middle here. And let's now hang it vertically. And it's a lot longer because it has a mass on it. Right? So, well, the reason it's longer is because we are now pulling on it with a gravitational force. And we know F equals minus kx. So if we want this mass to not move, it's got a gravitational force pulling down. Therefore, the spring force has to pull up. If the spring force is going to pull up, then the spring has to extend down, right? So its natural length was about here, and by letting it get longer to here, it applies a force that wants to make it shorter. And that force that makes it shorter is balancing the weight, okay? So the spring does get longer in its sort of natural equilibrium position. And you can actually then, if you want to consider this the origin, you can still apply Hooke's law. You just, in terms of doing a problem, you just imagine this is now the natural length of the spring. The natural length has been increased due to the weight of this mass. But it's actually still true, F equals minus kx. If we now consider this resting position the origin, if I pull down, say this is positive x, it pulls it back up in the negative x direction, right? I feel a force on the mass pulling it back up. If I push it up, it feels a force pulling it down, right? So it still acts like Hooke's law even when you hang it up vertically. And if you think about it, actually, if you pull it up a little bit, the spring is still pulling up, right? It's just the balance between the spring force and gravity is what makes the net force pull down, okay? So you don't have to worry too much about the details. I just want to let you know that when you put the spring up, you can actually apply the same equation, F equals minus kx, if you consider this the origin. Tension force is another one. I'm not really going to define it. I'll just say it is transmitted through a rope or cable or string, etc. So let's think about the tension force by considering this situation. What if I had hanging from the ceiling a long cable? At the end of that cable was a bowling ball, a big mass like that. I actually happen to have that right here. So here is a cable all the way from the top of the amphitheater, hanging down, bowling ball at the bottom, and it is free. It's not resting on the desk. It is sitting here, hanging just above the desk. So let's think, what's holding it up? Well, we got to do a free body diagram. Always do a free body diagram, right? So here's the bowling ball. Force of gravity, mg is pulling it down, and what's pulling it up, well, what's holding it up clearly is the cable. And the cable's doing it by applying a tension force. There is tension in the cable, and the sum of the tension and the weight in this case is 0. And that's why it's not moving in the y direction. So tension really is a property of a rope, cable, etc. Tension itself technically is not a force. It's actually a scalar property that is in newtons. It doesn't really become a force until you attach the end of the cable to something, and then it applies a force. So it's a property of this thing that applies the tension force to the ends, to whatever is attached to the ends. If you say, what if nothing is attached to the end? Well, if nothing is attached to the end, there won't be any tension, right? Two things have to kind of pull, or gravity or some other force has to put this thing under tension. And then it's simply a way to transmit that force to another object. Let's look at some properties of tension. It's constant throughout the cable. I'll just stick with cable. That's assuming nothing else is pulling on it on its sides. It's not going over a pulley and accelerating or anything. If it's just a cable with two objects on each end with forces, then it's constant. It applies it to both ends. I already said that. and the tension force is along the string direction. Right? If tension is really just a property of the string, it doesn't really have a force. To get the force, you have to think about the direction of the string and the direction it's attached to something. So we can see that a little more clearly if we go to another example, and that is our old mass resting on a surface. This, and the surface is down here, and we have a big mass resting on it. And I happen to have something like that. Right here is my little cinder block here, like that. Mass resting on a surface. Why is it not falling? It's not falling because mg is pulling it down, right? But the normal force, equal and opposite, is pushing it up. Great. Now let's apply a tension force to it with this rope. All right, so the rope is attached, and if I pull up, I could potentially ultimately cancel, or I could pull hard enough that I could lift it up in the air. And then instead of the normal force of the table counteracting gravity, it would be my tension force counteracting gravity. And I don't want to do that because I mean I could, but I don't want to. But what I want to think about is, what if we do this? So here I have a rope, and I have it under tension, and I'm pulling at an angle. So what forces are occurring? I'm applying a new force, and nothing is moving. Right, I'm applying a force, and nothing is moving. So let's draw the tension. Maybe you say, well, which way is tension applied? I don't know. So in this case, if the rope is at an angle, right, so here's the rope, and here's my hand pulling the rope, then the tension force, which I'll draw at the center, is also at that same angle. So the tension has a component up and a component this way. So I can draw the tension component horizontal and the tension component vertical. So the tension doesn't go normal to the surface, it goes along the direction of the rope or the cable. So what happens now, when I do this and it still doesn't move, you say, okay, the y component of the tension must make up for some of the normal force. So the normal force must go down a little bit. And that kind of makes sense. I'm kind of lifting it. So the desk doesn't have to push up quite as hard. But I'm also pulling it, right? There's some horizontal tension component. So why isn't it moving in the horizontal direction? We look like we have unbalanced forces here. We don't though, because remember, there's good old static friction. Even though it's not moving, there's a friction force pulling back. And that friction force will adjust. If you pull this way, the friction force will pull that way. And it'll keep it from moving, just like the normal force kind of adjusts to keep something from moving. If I pull hard enough at an angle, enough to overcome the static friction, then we can make it move. See? And then it goes. So there I pulled, notice I pulled at a lower angle to get more of my component horizontal. Therefore I overcame static friction and made the block move. So that's really it in a nutshell. In a problem, you'll often be given a cable and just being told it's under a certain tension. Apply that to whatever it's attached to. Or you'll be told it's hanging with a mass, and if that mass isn't moving, then you know that whatever the weight of that mass is the tension in the spring or string or cable. We heard earlier that Newton's laws always rely on an inertial reference frame. Blah, 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 in an inertial reference frame. So now we're going to see a little bit why, because we know that if you're not in an inertial reference frame, which basically means one that's not accelerating, one that's moving at constant velocity, if you're not, then you can have fictitious forces. So these are apparent forces you experience in an accelerating reference frame. And of course, the most famous example of this is if you're riding in an elevator, right? So here you are in the elevator, you can't see out, you have no idea what's going on, you're sealed in a box, and you hit the button and you tell it to go up, and for a brief instant, it accelerates up, briefly. And then you get near the top, and it accelerates, it decelerates to slow down, right? So if we were to plot the y position versus time for the elevator, it would look something like this. It would be sitting at ground level and then there'd be a little curvature while the curve does that, then you're going at constant velocity, and then a curvature while it does that. And you make it to your floor. We know we could take the derivative of this and get the velocity. We would know that this curved part is where there's acceleration. Oops. This is acceleration up, and this is acceleration down. And now think to your experience. What is it that you feel? You feel a force pulling you down when this happens, right? You feel a little bit heavy here, and you feel light here. So you're feeling a fictitious force, okay? So let's say the way you could treat this mathematically is in an accelerating frame. In the accelerating frame at the acceleration A frame, we'll call it that, A frame, Newton's laws work. I just said they don't work, but they do work if you do one thing. If you add a force to everything, F fictitious force equals minus m times the acceleration of the frame. Okay. So Newton's laws only apply to an inertial frame. Non-inertial, the one way you can fix it, all you got to do is add this force. It's fictitious. Why is it fictitious? Because it's not real. It's just because you're accelerating. If I'm in the lab frame and I watch this person accelerate up, I don't need a fictitious force. I know what's happening. The elevator applies a force to the person and they go up. The normal force becomes larger than their gravitational force pulling down. They feel a net force up. I'm in an inertial frame. I need no fictitious force. They are in a fictitious, or they're in an accelerating frame, and they need it. They don't know that the elevator is pushing them up. All they know is they're standing there, and suddenly they felt a little heavy. So this is really all you need to do these problems. Is if you want to solve the problem, just do your normal Newton's laws. Just add this force in here. Think of it as just another gravity force. It's just a constant force that applies to every mass in the frame. These will come up again when we get into rotating frames. The same idea applies in a rotating frame in part 2.